morning, everyone. I guess I could start out with Arakawa Margaret と申します。
This is Margaret Arakawa.
I am kind of a fake Japanese person. I'm American, but both my parents and 100,000 people that are related to me live in Hokkaido to Shizuoka. So it's very good to be here. I'm going to jump right in and make you watch this fantastic video. All right. So the rest of my talk will kind of illustrate some of the things that you saw in that video. Just a little bit of background about me. I've been in technology for about 30 years, which means I started when I was 5 years old. But I actually spent 20 years at Microsoft. I worked on every single commercial product that Microsoft sells, with the exception, I think, of a couple of products. But I worked on servers. I worked on on-premise, hybrid, in the cloud. I worked on databases, security, end-to-end networking as well. So I've spent my career and my lifetime, I interned at Intel as well. So I spent my career focused on what we call here in this particular trade show, classical computing. But what I'm doing at IonQ is to help, and our mission is to build the world's best quantum computers and networks to solve the world's most complex and impactful problems. This space is about solving very hard problems. And as we look at IonQ and what we're trying to amass, the reason why I show you this slide about patents is this represents the hard work of hundreds of PhDs and physicists that work at IonQ, as well as the companies that we have bought. But this is a massive amount of IP that has been generated for a very, very long time. And I'll show you sort of how long our journey has been. What we care about IonQ is about quantum being now. That's the #1 question I get asked at every conference I speak at. When is quantum coming? Do you care about NISQ or do you care about fault tolerant? Do you care about quantum supremacy or quantum advantage? What we care about at IonQ is these 3 things. We are focused, dead focused, as you always are in compute, on performance. Performance in every aspect that everybody in this conference has said, performance matters, for compute in particular. Scale, for us to scale. I started in the early mid-90s on convincing people the internet was going to be big. In the mid-90s, there was barely an internet. The internet was slow and it was insecure. But it was a journey that we took, and it rapidly caught fire, and it became the backbone of entertainment and everything else that we live and breathe today. Right now is the time to focus on performance and scale, but also we care about enterprise grade. It is the time to ship quantum computers, and it is the time to focus on quantum and commercial advantage. So we have been at this for a very long time. We have 2 incredible co-founders, Dr. Jung-Sang Kim, who was recently awarded pretty much a Lifetime Achievement Award in quantum, as well as Dr. Chris Monroe. They had done a lot of work in quantum at both Duke University and University of Maryland. What's incredible, I should have put dates, but at the very early part, the year that we started, and we've had that first breakthrough of logical gates on a trapped ion computer, what year was that? Was it 5 years ago or 10 years ago? It was 30 years ago. That's how long this company has been working on building from What you see from a lab, experiments, academic demonstrations, R&D, on focusing on both scientific outcomes and business outcomes. And we are at phase 5 now as a company. We are focused on delivering business value. We're focused on delivering production machines, deploying them so that they're available, they're interoperable, and as everyone has said in this conference, the world is going to be hybrid. There's going to be a CPU, a GPU, and a QPU. They will be all needed, they will all work together, just as right now, the vast majority of companies are on-premise, hybrid, and cloud. That will still exist, and I think it'll exist for our lifetime. IonQ has been delivering quantum computers for a while. We went public. We're the first pure-play, publicly traded company on quantum in the United States. We went public in 2021, but as I said, we started in 1995 as far as our hard work on the academic and the scientific discoveries. We are on our 4th generation computer, and we will be delivering our 5th generation computer shortly. So as you see, we have had this roadmap and we've been publishing it for quite a long time, and we've been consistently delivering on our results. Right now, we actually have Forte Enterprise, our 4th generation computer. It's now globally available. We sell our computers not just on-premise, but also via the cloud. And AWS Bracket is an incredible partner of ours. And they're very excited that they have multiple generations of IonQ quantum computers that you can access now via Amazon and AWS Bracket. So as I said, we're a company that sells quantum computers. We also sell all of those, as I said, on our cloud as well as Microsoft Azure and Google Cloud. We're the first company and one of the very few on earth that you can access via all the clouds. And the reason this matters is we want to democratize quantum. We need more developers. We need HPC people to learn quantum. We need people in universities to care about quantum. And we need to make it easy to access. This is not a monolithic thing where you have to reserve time on a mainframe. This is about getting access to quantum computers today. We also build a software stack, very classically the same as when I worked at Microsoft and we were building from the BIOS all the way up. Quantum computers has that middle layer, and it's required in order to do the hybrid services, in order to work with the GPUs. So we have that layer, and then Masako will be talking about the commercial applications and the applications team that we actually work with. The other thing that makes us very different as a quantum computing company is we're one of the very few on earth that have quantum computers, the full stack, as well as a quantum network. We acquired a company that has already built out a quantum network in the US. And so this is a big strategic opportunity for us. So imagine, if you will, long ago, there was an HP or a Fujitsu Toshiba, then there's a Microsoft, then Intel and AMD and all of the providers in that layer. There was also a Cisco and an NVIDIA that then, perpetuated both the internet as well as compute. Think of it in that way. Quantum is going to be growing in that same way. IonQ has been expanding our global footprint very, very rapidly. As you can see by the flags there, we have locations in the US, Canada, as well as Switzerland and in South Korea. We have built and grown through both organic growth as well as acquisitions. And again, those acquisitions are to build out that entire infrastructure from the hardware, the software, the applications, and the quantum network that everyone will need, because we are building, and is happening now, the quantum internet. These are a select number of our customers. As you can see, Hyundai, which is a very, very large car company, obviously. We've worked with them for a very, very long time across many different problems and challenges that they've had to really look at HPC and what it did, and then what can quantum do above and beyond that. Airbus, we work with them on optimization. NVIDIA is a big partner of ours. Our CEO was just at GTC speaking with Jensen Huang on stage. Again, all of the hyperscalers. AFRL is the Air Force Research Lab. We have almost $100 million of contracts working with the Air Force because they're focused on secure communication. So you can read the rest of it, but what we really do care about, again, is building and delivering value as well as systems. NVIDIA, not only do we work with them just to work with them because they're, they have CUDA, but they also have CUDA-Q, which is their way of interacting between classical CPU, GPU, and QPU. We actually worked on an application with them that is actually an incredible seamless ability to integrate the core workflow. And so imagine NVIDIA is very focused on having both the CPU, GPU work together, but as you can see, but from their former presenter, they do care a lot about the seamless workflow through to quantum. We also announced a partnership with AstraZeneca. AstraZeneca is one of the largest pharmaceutical companies in the whole world. And we announced a partnership with them because we have quantum expertise, but they have pharmaceutical expertise. And everyone here knows one of the dreams of quantum is that we are going to accelerate drug discovery. We are going to focus on the chemistry and the construction and deconstruction of molecules in order to find the cure for cancer or the cure for any of the diseases that we still don't have cures for. Quantum is very able to look at that hard problem and give us very, very early signs of incredible outcomes that we know that we will have in our lifetime. ANSYS is a company that focuses very much on HPC as well as CFD. They work with almost every industry in the world that cares about computational fluid dynamics and about making sure that the cars that are built have the research against them to make sure, and actually Masako will be talking a little bit more about that. So I'm gonna head into the discussion I had about generative AI. And the topic is bigger always better? And what's the opportunity here? So everyone here probably knows about LLMs. LLMs from a consumer perspective, most of us stumbled upon LLMs in what? ChatGPT. It's a large language model that is the basis for ChatGPT. Another part of AI that we have been, as an industry, working on is generative adversarial networks. Probably the most famous was when there was an experiment to try to see if Pac-Man could be actually worked out with this GAN without any instructions. So these are some of the elements and the backbones of the problems and the technologies being used for generative AI. These businesses are gigantic. They're very, very large. $8 billion for LLMs, and for GANs, $2.5 billion. So these are large industries from an AI perspective that are growing rapidly. So I'm going to quickly go over some history about LLMs in particular. In 2019, Google actually introduced BERT. It had 240 million parameters. It was the largest LLM at the time. And then later that year, OpenAI released ChatGPT-2 with 1.5 billion parameters. That's about the amount of energy needed to run this was about a trip on an airplane from Tokyo to Honolulu and back. So not a lot of energy. But then ChatGPT-3 came out in 2020. And now you're at 175 billion parameters. And that's when you have very, very large numbers from a parameter perspective, bigger data sets, longer training cycles, but great performance. And then you have this massive 500 billion parameters that Palm introduced on the LLM that they built. And then when you get to ChatGPT-4 announced in 2023, that's the first trillion parameter generative AI-based LLM model. So when you get to that point, it turns out that the International Energy Council basically realized the impact to energy would be severe. The amount of energy that's at this point, and as we get into 2026, all LLMs in the world, the energy that they need is going to be the same amount of energy needed to actually power all the homes in the entire country of Germany next year. So the energy problem is today, and it's going to be massive tomorrow. The nice thing is we have companies and technologies like DeepSeek that are shrinking down the number of parameters. So we have big is better, but sometimes as we get smaller, we're going to get more fine-tuned, and we're going to work together with QPUs that are going to work with the CPUs and that work with the GPUs. There's a lot of great opportunity from a classical generative AI perspective versus quantum generative AI. And I would just leave you with this. Large models love very, very big, representative data sets. They're very expensive though. The smaller models, they struggle with that smaller set of data, but they're more cost efficient. So quantum generative AI, working with small models, we believe that that's where we can all work together to have a cost-effective model for how we actually grow the generative AI model market, but without crushing it from the data needs and the electricity needs. So I'm going to quickly go here. and just say, one of the things that Masako is going to talk about is how did we work with some of the biggest companies in the world on some of their tiny problems or their minuscule problems. Every manufacturer of steel, like car companies, they care about the defect rate in their steel. So they need to look and get electron microscopy to see whether or not there are any early signs of defects. So the side over there, that should be my hair, it should be gray. But 10 micrometers versus 70 micrometers. A micrometer is 1/1,000,000th of a meter. So the images that they have to take are so small and so expensive, and they are so rare that it's very hard for them to detect defect rates very early. So I'm going to hand it off to Masako for her to talk about it.
Thanks, Margaret. So my name is Masako Yamada, and like Margaret, I'm kind of a partway Japanese person. I was born in Japan, but I grew up in New York, and I did attend Japanese schools to the end of high school, so I am understanding what you're saying, but I lived in the US and worked at American companies since. So if I can introduce myself, my academic background is in HPC, classical HPC, and I've spent 30 years in that field. And really, why was I motivated to move to IonQ 3 years ago? So I was invited by Jung-Sang Kim, one of the co-founders, to join IonQ to basically productize some of the next generation hybrid quantum algorithms that the company has been developing. So this is one example of a hybrid quantum algorithm that we've been developing in partnership with one of our customers, as Margaret had mentioned. And what we are doing here in this activity is, when you think of machine learning, what you think of is a huge amount of data. And if I were to think of a classifier of cats and dogs, billions of images of cats and dogs. In industry, it's actually quite hard to collect billions of data on anything, especially if it's so hard to capture the data, as Margaret had mentioned. And the especially hard part, I worked at GE for 20 years. I know Six Sigma processes. If you work in an environment that adopts a Six Sigma type mindset, you have very few defect data. So what do? If you want to train a machine learning model? One, the absolute amount of data is relatively small, and two, the amount of defective or minority data can be very, very small. And this is the challenge that we sought to address here. Okay, so this is the GenAI workflow, a classical GAN workflow that anybody can use, has been in industry for maybe about 5 years. And what we did here is to ask ourselves, is there an opportunity for quantum to add value to this workflow? So basically, we just substituted one module with quantum. The rest of it is still classical. And that is why we call this hybrid, right? We're changing just one module within the workflow. What do we find here? So using this hybrid algorithm, what we did is we compared our results against a classical benchmark. We used classical GANs to generate the images. We had a sort of quality metric, an image quality metric along the y-axis. And we had a certain, classical benchmark image quality metric, which we've normalized to 0. And then we look at the quality metrics of the images generated using this quantum hybrid GAN model. And as you can see here, already we see, using the number of qubits that we have, some improvements in the image quality using hybrid quantum GAN versus classical, which is the blue benchmark. And this is just one of the examples of a type of problem class that is very important to industry that we are attempting to solve using hybrid quantum algorithms. The other problem that is really crucial to all of us, as Margaret had mentioned, is the energy issue. And as Margaret mentioned, LLMs are very greedy. They want all your data and all your energy, right? It's infinitely hungry. And this is a picture of 3 Mile Island, which is a nuclear power plant that was actually decommissioned, I think in the 80s, and it is being recommissioned to run one of Microsoft's data centers. So they literally are using a nuclear power plant to run a data center. At the time, this power plant powered a substantial fraction of the state of Pennsylvania. So this is not a small energy generation source. And also coming from GE, I know that currently gas turbines are selling like hotcakes. Why? To power AI. So it is an incredible opportunity for energy providers, but also a question that all of us can ask about what can we do to address this. So this next paper, which was published about a month ago, or the preprint was posted about a month ago, is around using quantum machine learning to fine-tune an LLM. So what did we do here? When Margaret showed the LLMs, she showed BERT, which is from 2019. At the time, it was the largest LLM. What we did here is we took BERT, already trained, all the parameter weights are there, and then we asked ourselves, can we do a fine-tuning, a last layer fine-tuning using quantum machine learning to have it do something different? So basically, to step back a bit, what does BERT do? If you have a sentence and there's a blank, it will fill in that blank, right? The quick brown fox, is it brown fox? If you have a phrase and you can just have a space, it will fill it in. So that is what BERT does. What does fine-tuning do, or what can fine-tuning do? In this paper, what we do is we take a pre-labeled set of about 256 sentences with sentiment labeled. So if a sentence, it reads it in, is the sentiment positive or negative? Just 256 sentences. We do a fine-tuning of the BERT model, and now this model can detect sentiment. So you put in any sentence into it, and it will basically classify, is that sentence positive or negative? Again, what we do is we take a classical model, which is a classical foundational LLM. We really don't do anything new to it. What we are doing is we are now adding a quantum last layer to make it do something different. What are the results? Again, as before, we compare it against a classical benchmark. So we do the same fine-tuning using 100% classical methods. And then we see that our hybrid quantum algorithm is actually able to get better classification accuracy compared to 100% classical methods. Now, we've only shown this up to a maximum of 16 qubits. This is simulated. But as we increase the number of qubits, the aspiration or hope is that the classification accuracy continues to improve or increase. And this is really what the problem that all of us, I think, are trying to solve, which is as we get bigger and better quantum computers, can we realize more benefit from a performance point of view? And finally, circling back to the energy problem, we also did estimations of energy consumption of classical versus quantum training. And here we see a crossover point at around 46 qubits, where we have estimated that the energy consumed by classical methods and quantum methods will flip. This is yet to be verified, but we are committed to starting this month to do actual measurements of power consumption as we do these calculations. And we hope to be able to publish these results soon, as we will be starting the measurements this month. So thank you so much. We do have a booth, so please come visit if you're interested in further conversation.